Okay, welcome back. We're moving on to section 12.2. This is called Surfaces as Graphs. I don't think that's a very useful title. We're basically talking about tangent planes today, so I would probably call the title here Tangent Planes to Surfaces. And why do I say tangent plane? We're just going to jump over to the whiteboard really quick to try to describe what's happening. If we jump back to our generic calculus, there's maybe a function f of x, and in particular this is y equals f of x. It's a function, and in calculus we would grab a point on that function and we would define tangent line to curve at point. Okay, basically what is the higher dimensional version of a line? It's a plane. Okay, so if we're now going to be graphing maybe on a surface instead, let's give myself the paraboloid. It's a classic surface. So here's a paraboloid. Let's grab some orange here and just kind of fill the surface in. Okay, so there's our paraboloid surface. If I want to talk about the higher dimensional analog of a line, I'm going to grab a point on the surface, and now my surface kind of has locally looks like 2 dimensions, and so there's some sort of plane passing tangent to my surface at that point, and the plane is the tangent plane to surface at point. Okay, so we're going to ask ourselves, can we actually calculate these? Because the same sort of information we might interpret from tangent lines, we can interpret with tangent surfaces. So that's what this section's on. I'm going to highlight really quick right here, y equals f of x, and actually let's jump over here as well. This was z equals f of x. Y, right? If we interpret these, we can reinterpret y equals f of x as y minus f of x equals 0. We can reinterpret z equals f of x y as z minus f of x y equals 0, in the sense that now these interpretations are just like our last section where we interpret those as level surfaces of some higher dimensional function, and we're choosing the specific surface value of 0, right? And then the left-hand side in both cases is our higher dimensional function. So that's how the last, section leads into this one a little bit. Let's leave the whiteboard. Okay, so let's just take a really quick example and try to refresh ourselves on Calc 1. Calculate the tangent line to that function at a specific point. How we do that is we calculate the derivative, and the derivative will be 4x here at x naught equals 3 gives 12. And we interpret the 12 as the slope of tangent line. So now that we have a slope 12, we need a slope, and point gives line. So my slope was 12. My point here is 3, f of 3. Which if I evaluate f of 3, I guess I get 18 plus 5 is 23. So y equals 12x plus b. What should b be? Well, I evaluate y equals 12 times 3, gives me 36. I need to recover 23 instead of 36. How do I recover 23 instead of 36? You subtract 13. So there's my tangent line at the point. We're going to do something very similar with the plane. Now, jumping back, we need an equation for a plane. I'm not entirely sure if you covered this in the first semester, but if you haven't, we're going to introduce it right here, okay? So we're going to talk about what does it mean to describe a plane in R3. Okay, and there it is. So describe a plane in R3, in 3 dimensions, a 3-dimensional plane, just like we would have, y equals mx and we could rewrite something like y equals mx plus b, rewrite as mx minus y plus b equals 0. Right, we can basically rewrite that equation as now as an implicit equation of both x and y on the left-hand side, and then it's equal to 0. Basically the same things are happening here. A is like m, b is like some other slope, c is one more slope. So we have slopes in the x, y, and z directions, and then the plus b from our earlier equations, just like this plus d. So it's this idea of like a higher dimensional linear equation. This is about as abstract as we can get. Okay, so that's the generic equation for a plane, and we would find the values for A and C very easily by calculating the change in the x direction of the plane. What is the slope in the x direction? What's the slope in the y direction? What's the slope in the z direction? Right, if we calculated the gradients of partial derivatives of this, we would get A, B, and C respectively, and then more importantly, what is the I guess you could call that the intercept. So the z-intercept. If we let x and y be 0, where does the plane intersect the z-axis or something like that? So that's we would go through the same sort of procedure to find all of those. Basically, we need 2 slopes and 1 point to define a plane. Why 2 slopes? Well, a plane has 2 directions which it occurs in, and then the point describes the intersect. So that's what we're always going to search for when we eventually want to find a plane, is 2 slopes and 1 point. There's also something interesting about the equation for a plane. We can either represent the equation for a plane as an equation, or we can represent it under what's called a surface normal, right? Because if I define the vector which points perpendicular to the plane, that actually perfectly describes the plane as well. There's only one plane in 3 dimensions which is perpendicular to any given vector, and the way we would calculate that is by computing the gradient of the function. Once again, we consider this as an implicit function and the level curve of an implicit function. So we calculate the gradient here. Partial x gives me a, partial y gives me b, partial z gives me c, and the d disappears from each. So our gradient is abc. Dividing by the magnitude, we divide by root a squared plus b squared plus c squared. So this is always going to be the surface normal vector to any given plane. And here we've provided a diagram. So for example, we can see the plane, which extends in some ways left and right, and the surface normal, which points exactly perpendicular to that plane. Okay, so now that we know how to maybe construct a plane, or at least in general, the idea of a plane, we will actually start to construct these tangent planes and surface normals. Okay, so I'm going to jump down to this right here. It says if we have a surface, so sigma is a Greek capital S for surface. So if you have a surface given by, now this is a little vague, x, y, g of x, y. Let's retranslate that. What is that actually saying? This is the graph z equals g of x, y. Okay, so we have some scalar field, which is a function of x, y. Something like cosine xy plus xy squared, for example. Okay, so you have some scalar field, which is a function of x and y, and we're going to assign that to z. Okay, that's saying this is the x, y, and z coordinates in 3 dimensions. The graph z equals g of x, y is what we're dealing with. So the surface is given by that graph. Then we can compute the plane which goes through that surface by computing the following. So we're going to compute a curve which is parameterized by x now. So the curve cares about the x coordinate. The y coordinate has been fixed, okay? So the y coordinate's been fixed. Recall this is x, y, z. X and y are themselves. Z is g of x, y. So now how does the curve which passes on my surface depend on x, y, and z? Well, exactly, x is being left free, y has been fixed as k, and z, which happens to be the same as g of x, y, I'm going to plug the x value in to g, and I'm going to plug the y value, which has been fixed at k, into g. I want to think about this as this is a curve at y equals k in x direction. Okay, so if I calculate that curve, I can compute its specific tangent vector, the tangent vector strictly to the curve, by taking a derivative. Okay, if I take a derivative of that curve in the x direction, it's very clear that what is the derivative of x with respect to x? Well, it's 1. What is the derivative of k with respect to x? Well, it's 0. What is the derivative of g of xk with respect to x? Well, the k, it doesn't care about that at all. So all I'm doing is taking the partial derivative of g with respect to the x direction. So I have this vector 1, 0, partial g, partial x. And that's my tangent vector. So I want to think about this. Tangent vector at xk, but specifically in the x direction. Okay, and for a plane, I'm going to need the y direction as well. So if I want to calculate the tangent vector in the y direction, I go through the exact same process. And that gives me that the tangent vector in the y direction is 0, 1, partial g, partial y. Okay, so this is what we want to think about. I went through a little bit of too much work to end up with these. These are our two tangent vectors at some point x naught, y naught in the x and y directions respectively. And that's very useful because once I have two tangent vectors and a point, right, two tangent vectors and a point, then I can construct my plane. So scrolling down just a little bit farther, the plane gets constructed, the plane passing through the point x0, y0, and wherever it ends up on the surface gets constructed by what is the slope in the x direction. This is now in point slope form, by the way. What is the slope in the x direction at my point? What is the slope in the y direction at my point? And then I take the z value and subtract the z point. So let's just make this a little bit more clear. That's an x value, so x point goes right there. I mean, there's a negative sign, but it goes right there. The y point goes right there. The z point, which you'll recall is g evaluated at x and y, goes right there. And finally, I end up with my x slope and my y slope. So that's what we want to think about here is our overall plane equation is point slope formula where I have the z point. This is how z moves against its initial point. I have the x slope and then multiplying x minus its initial point. I have the y slope multiplying y minus initial point. Okay, so I would definitely just stare at this for maybe 5 seconds or maybe screenshot or write this down somewhere. This is what we want to think of basically for the rest of this section. Okay, hopefully that was enough time for you. I'm going to move, right? There's one other important thing in this section, that's the normal vector. So how do we compute the normal vector to the tangent plane? Well, it's the exact same as what we did before, where technically, if I want to, I can take the cross products of the directions in both the x direction and y direction and then normalize that. But if I actually go ahead and compute what that would give me, it's going to compute the following. So I would have the negative derivative in the x direction, the negative derivative in the y direction. The z direction remains constant because it's going to be pointing normal basically to the x and y directions, right? Those are the directions we care about. And then I'm just dividing by the magnitude of that vector. Okay, so maybe we pay attention to this too. So here's really our two definitions for today that I want you to pay attention to, or all of these under here, for our plane in the first case and our normal vector in the second case. Don't worry about this part. That's kind of superfluous. Okay, because now we're going to actually compute them on one example here. Let's consider this function, f of xy is negative x squared minus y squared, and we'll jump over to the whiteboard. And so our function of x and y, which happens to be z, right, is negative x squared minus y squared. Let's calculate tangent plane at x0, y0. We'll calculate normal vector at x0, y0. All right, so starting out with the plane, we recall our formula was z minus the value that z takes at the point, which in this case is f of x naught, y naught. And then it was partial f, partial x at the point. So this is the slope in the x direction. And then x minus the point it starts at. The slope in the y direction, y minus the point it starts at. So we just need to calculate a few things. We need to calculate the partial with respect to x, the partial with respect to y, and the value of the function at the point. So let's just grab those three things. Partial f partial x is negative 2x. Partial f partial y is negative 2y. Finally, f of x naught y naught is negative x naught squared minus y naught squared. And so if I plug each of those into my equation here, negative 2x needs to be evaluated at x naught y naught. Negative 2y also evaluated at x naught y naught. And then I have my function value there. If I write all those out, I get z plus, because the pluses are canceling with the minuses, x naught squared plus y naught squared equals negative 2x naught, x minus x naught, minus 2 y naught, y minus y naught. Okay, so all I've done is I took that negative 2x, I evaluated it at x naught and ended up there. That's why I have negative 2x naught there. I've taken negative 2y, evaluated at x naught, y naught, and put it there. And that's why I have negative 2y naught there. Everything else came directly from my equation. And there it is. There's the equation for the tangent plane. This could and probably should be simplified. This could and probably should be simplified. But by and large, that is now my equation, because I have my z, x, and y variables, and everything else is a constant, even though x naught, y naught has not been defined yet. Okay, jumping down to the normal vector, let's recall the definition for the normal vector. N was 1 divided by root 1 plus partial f partial x squared plus partial f partial y squared. And then I ended up with negatives in front of partial f partial x, negative partial f partial y, and z was 1 because in some sense, what is partial f partial z when f and z are the same thing? It should be 1, right? Let's erase some of these. Okay, so we've already calculated the partials, which is really nice. So partial f partial x is minus 2x, partial f partial y is minus 2y. So I'm just going to plug each and every one of these in to my normal vector equation, and I recover all of this, by the way, is use a new color here, all at the point x naught, y naught. Okay, so we do have to evaluate each of those at our specific point. But jumping back to just evaluating, I have n is 1 over root 1 plus, now this is negative 2x naught squared, and that's negative 2y naught squared. Those are coming from my partial derivatives, which I've already calculated. Up here I get 2x naught, 2y naught, 1. I can simplify the denominator a little bit, but not really that much. It'd be 1 divided by root 1 plus 4 x naught squared plus y naught squared. And then these have to be the same. 2x naught, 2y naught, and 1. Okay, so there is my normal vector to the surface. That one cannot really be simplified, but the nice thing in these forms is if I want the tangent vector at the point 1, 2, then I just let x naught be 1 and y naught be 2 everywhere in the formulas, and I immediately recover the tangent plane. Same down here, if I want x naught to be 1, y naught to be 2, I just plug them in and evaluate, and I immediately recover my normal vector. Okay, so let's jump back to the book. And we can see the same answers we recovered earlier for z as well as n. The book has a typo here. These should be plus signs, right? If I'm squaring a negative sign, these should both be plus signs. So the book has a slight typo there. You'll know that you made the same mistake if you have the chance to divide by 0. You don't want to divide by 0 here. It should always be positive. Anyway, that's all I have for today. We'll work more in class. See you there.